So yeah, the title is comparing conditions under uncertainty. So this is about comparatives and conditionals. I think that we have experts here on conditionals and comparatives here, so it's great. So yeah, so there, I think this has been done mostly in the linguistic literature lately. So people have been working on how comparatives interact with quantifiers, and there are several popular proposals which addresses certain issues in the interaction. One of them is based on in intervals, and another is based on degree phrases as being a generalized quantifier over degrees. And there's also another line of research where you have an existential construction over degrees with negation, like interacting with the quantifier. So yeah, what linguists have looked into are examples like John is taller than everyone else is. The paper is required to be exactly 5 pages longer than that, and so on. And I'm gonna in this talk, I'll probably talk about just this sentence. I might have one or two more sentences, but it's basically this: if Adam takes the lead, the organization will be more successful than it will be if Bill takes the lead. So I'm gonna claim that this poses an issue in existing theory. So on the interaction between quantifiers and comparatives. And I will eventually claim that this can be accounted for. At least there will be a working solution once you drop the hypothesis that conditionals are quantifiers over SS labels. So a short background, so I don't have much time, so it's very, very, very short. So let's start with example 4. So when you have John is taller than every girl is, Schwarzschild and Wilkinson pointed out that this would be an issue once you take syntax theory. So the intended meaning of John is taller than every girl is that you have a universal quantifier scoping over everything else. You have to have say for each girl, for each x, if x is girl, then John is taller than x. The problem is that the then clause is a finite clause, and since being a finite clause it's a scope island, and you normally don't expect a universal quantifier to scope out of the finite clause. It can't take over the scope over the maintenance clause. And in the Schwarzschild and Wilkinson theory, we can account for this based on intervals. So roughly put, if that 4 is true, if and only if there exists an interval I, such that John is I false, so John's height falls into this interval. And the larger interval j, which is some distance away from I, contains every girl's height. So you're going to have an interval containing John's height, you're going to have an interval containing every girl's height, and there is some distance between these two intervals, something like that. And Heim 2006 accounted for Schwarzschild and Wilkinson's data while assuming that degree phrases are generalized quantifiers. So here, what Heim does is you basically scope the item. This is one popular technique. So you're not going to let the universal quantifier scope out of the finite clause. Rather, you're going to, since finite clause is an island, you're going to move that up, the entire island up, and then the universal quantifier will be just taking the highest scope within that finite clause. So you can see my mouse pointer. So every is here. So this is embedded clause. Every girl is, and this itself is an island. It has range from down here to up here, taking the highest scope. And within that island, there's a universal quantifier taking the highest scope. And then what you get is, so this is, I don't think I should go through this, but I'll just explain briefly. So Heim has this pi operator, which gives you a certain scope of relation. That basically gives you a certain scope of relation. So this pi basically says it will take 2 arguments, 2 sets of degrees, one here, the other one here, and says that the maximum value of the second argument is a member of the set of degrees denoted by this. So what this amounts to is so you're going to get the maximum value of John is tall, that's actually John's height, and then this ER then will correspond to the set of degrees, greater than, shorter than. Alright, it's one layer, so or then that, so or then the set of degrees greater than the degree assigned to the trace, and as a whole, this will eventually mean correspond to the set of degrees shorter than John's height. And on the right hand side, you have every girl, you have the pi operator, you have the grade of actives. And what this will give you, again, this will have two arguments, one here, the other one here. And this will correspond to each girl's height. And this trace will correspond to the right hand side, which is a set of degrees shorter than John's height. What you get as a result is that you say for each girl X, X's height is a member of the set of degrees denoted by the right hand side, which is a set of degrees shorter than John's height. And that actually makes sense. Very complicated. I did have to go through this because I will just adopt Heim semantics later on to show the point out the issue. So one issue with Heim theory is that it generates unattested readings, as it predicts that a quantifier and the pi operator can freely take scope over each other. So it will basically over-generate. And Schwarzschild 2008 offers a solution to this overgeneration problem, where you basically partition the domain of individual into positive and negative extensions, and you're going to insert a negation in it. I'll just explain what this means. When you have John, Todd, and Bell, the truth condition will be the following. So we're going to say there exists a degree D such that John is tall. John is at least as tall as D. Basically, John has height D, and it's not the case that Bill meets this height D. Right? So there's a degree D. John meets that height. Bill doesn't meet that height. Negation is the right concept. John is taller than D, at least as tall as D. Bill's not. That's how you say John is taller than D. John is taller than Bill. What's important here is that this negation can move around, so it will interact with the quantifier. So so when a quantifier appears in the net clause, it will interact with negation. And what Schwarzschild claims is that these scopal possibilities mirror the over counterpart. So suppose you have an interaction with supposed to be and negation. As an AP, John is not supposed to miss the lab meeting. It only has one reading where the numerical quantifier scopes over the negation, right? And that will be reflected in the comparative construction as well. When you say John is taller than he's supposed to be, there exists a degree D such that John is D tall, and for all, so you're going to have a quantifier here. For all accessible in each deontically accessible world, the negation is placed within the universal quantifier. And you say that in each deontically accessible world, John's height does not meet that degree. What does it mean? John is taller than he's supposed to be. So that will give you the reading where John is actually too tall, right? I'm not a native speaker, so I always have a hard time. Yeah, in every deontically accessible world, that John is not D tall, so that's like above the permitted range of being tall. So like suppose that John is like 9 years old and he's trying to ride a baby roller coaster or something. You just have to be shorter than a certain height. John is actually over that. That's when you use 8. On the other hand, consider 9A, Mary's taller than she has to. Has to be usually takes scope below the negation, as in 9B, Mary doesn't have to come to the lab meeting, doesn't have to. Not necessary, right? So and that will be reflected in the comparative result. So Mary's taller than she has to be. There exists a degree D such that John is basically D tall. And it's not the case that the negation is actually higher than the quantifier. Then you basically say that it's not the case that in each deontically accessible world, John meets that height. So John is taller than minimum, right? That's the minimum required height. And Mary is actually over that. So like Mary's trying to like write a scary poster, and she has to be can't do inches and feet anymore. She has to be like 140 centimeters tall, and she's actually over that. There are issues, and should have mentioned to Gajewski Forkis law, but yeah, you guys already stuff on it, but I will just go on. So yeah, but there's issue with just using this negation, and that's what Ren actually point out. And in some cases, the negation can go over or below the quantifier. As in 10, Frank's income is higher than it needs to be to qualify for this deduction. You get both the maximal reading and the minimal reading, depending on the context. And yeah, so Ren can use negative quantifiers instead of just pure negation to talk about this. But yeah, I want to go through that. Instead, I'll move on to Beck. So Beck's analysis, I'm not sure how to categorize this, but it's very contextually determined analysis, where she says, so you basically have an interval like semantics within the Dan class, as in Heim. But what the Dan class return is not just an interval. It's actually a single degree. How do you do that? You basically have a definite description like element in it, and when she says that you're gonna feed that interval into this function and in maximally informative interval. So you feed it in, and you're gonna figure out what is the maximally informative interval, meaning that it's the shortest interval that satisfies certain condition, and then you're gonna pick out the highest, should I say highest, the endpoint of the interval, and that is the interval. That is the degree that will be used in a comparative construction. So so suppose that you have like John is taller than every girl is. Well, say John is taller than every girl is, you're gonna have an interval that contains every girl's height, and then you're gonna find the endpoint, which is the tallest girl's height, and that height will be used to compare these compare it with John's height. So you're not using the entire interval, you're using a single theory. And the advantage of this analysis is that this ordering of degrees can be determined contextually. So that will kind of address this issue regarding like something like needs to, where you can have to both minimal reading and the maximal reading. Not necessarily where Frank's income meets the minimum required income, or it actually exceeds the maximum permitted income. So you can get these reading when you rely on context in ordering these degrees. So when you say Mary wants to play basketball, the school of rules requires all players to be at least 170 centimeters tall, and you can get how does she has to be the minimal reading, where in Mary's college she has to be by saying that this is basically what Beck does is that she kind of relates to a sufficiency modal construction. But what she ends up saying is that meeting the like minimum requirements is actually at the end point rather than the maximum, and that's actually determined. And so here, although 170 centimeters tall is actually shorter than being like 173 centimeters tall, the ordering regarding this interpretation is actually reversed, and the maximum point, the end point, will be 170 centimeters tall. So she has this flexibility. So you can reverse the ordering based on context. So this is a quick review. And what I'm gonna argue is that they all don't seem to work. So regarding the initial conditional comparative construction, I'll give two concepts. One is what I call the dominator. So, and here it is. Adam and Bill are competing for the leadership of an investment organization. Adam has consistently made better investment decisions than Bill. Both of their strategies, however, are sensitive to the outcome of the upcoming presidential election. If the leading candidate wins, both Adam and Bill are expected to do well, with Adam clearly outperforming them. If the underdog wins, both will face challenges. It's thicker, but again, Adam is projected to manage the downturn more effectively than Bill. Still, the gap between their best and worst cases reveals an important asymmetry. Adam's worst case outcome, which is under the underdog's presidency, yields less profit than Bill's best case scenario, where the leading candidate is. So in this context, if Adam takes the lead, the organization will be more successful than it will be if Bill takes the lead. It's true. I don't think there will be any disagreements. So yeah, I should have used the board. But you get it, right? So in the best case, when you compare the best cases, Adam performs. Even when you compare the worst cases, Adam is better than Bill. But when you compare Adam's worst case to Bill's best case, Bill's better than Adam. That's one context. And here's the second context, which I call the deliberate risk taker. Adam is a risk taker, in general, a highly successful one, and Bill prefers to play it safe. Adam's strategy is to invest in certain stocks whose prices may surge. Adam's strategy is to invest in certain stocks whose prices may surge or drop depending on the outcome of the presidential election. But a series of public surveys unanimously suggests that the odds are in favor of Adam's plan. The leading candidate has publicly announced plans to provide substantial financial aid to the semiconductor industry. In which Adam is planning to invest. We believe that the organization is highly likely to thrive under Adam's leadership, though there is still a small chance his investment could fail. On the other hand, Bill's decisions won't be affected by the presidential election. We believe that the organization will profit to some degree, but it won't be nearly as successful as in Adam's best case, and which is also the most likely scenario. Yet the organization will fare better than Adam's worst case and fairly unlikely scenario. So you get the point, right? So there's like a high chance that Adams will be better than Bill, but there's still a slight possibility that Bill will do worse than Bill. So in this context, I actually would like your judgments here. 16, if Adam takes the lead, the organization will be more successful than it will be if Bill. So several options. True. First, I can't tell. Acceptable, assertable, not assertable, not acceptable. Who thinks this is true? False.
I'd say that 16 is pretty credible, but not
very credible,
but not not one.
Are you a linguist or a philosopher?
Linguist.
Linguist. Semanticist or
yeah.
That's it?
Yes.
Oh yeah, both of them. So I asked around. So usually syntheticians and P-side people say it's fine. If you ask a semanticist, they have a hard time. If you ask a philosopher, they usually say I don't know. You can't tell me. Something like that. So I'm open to any, as long as you don't say it's false, outright false. So I can't tell from that. Yes. So yeah, I mean 17, I'll skip it for now. So yeah, so and these are the two the main contexts I will be evaluating the sentence on. And I'm going to use Heim theory to point out the issue. Well, it's actually, I think, the most flexible among extent accounts, and well, too flexible to a point that it overgenerates. but you don't have to carry out over generation here, right? So because the point is to say that you cannot derive any, it cannot derive into the reading. And yeah, so I've also discussed alternate theories, very appropriate. So some syntactic assumptions. So the second conditional is a then clause, and that and there will be 6 possible LF configurations, which vary with respect to the scopes of the pi operator in the matrix clause, the pi operator in the embedded clause, and the scope of the then clause. It happens that they only produce 2 distinct readings. So here's the first LF. You can see that the pi operator is scoping below the matrix model, and the then clause is actually higher up. And within the then clause, the pi operator is scoping above the embedded model. I'm going to assume that if clauses are restrictors, and it just merge if clause with the model. And what happens? So I'll just use this LF. So here, so this pi operator will take the second argument and get the maximum degrees of success. In which row? In a row where Adams takes the lead. You get Adams success, and this is a set of degrees less than or equal to the Adams success, and you're going to have a model on top. And as a whole, what you get is you're going to get a set of degrees that's contributed by this index 2, set of degrees such that any epistemically accessible role in which Adams takes the lead is such that this degree is less than the organizing success in a world where Adams takes the lead. Which is basically the set of degrees that is worth less than Adams' worst case scenario, Adams' success in the worst case scenario. Do you get this? You say, yeah, there will be a degree that will be satisfied by this. And you say in every epistemically accessible world, you compare that degree to the organizing success in that quantifier world. And it has to be that in every single world, this degree D should be less than the success in those quantified worlds. And then you're basically comparing this degree to the world where Adam basically fails and is in the worst case scenario. Compare these two, and this right hand side will denote that set of degrees. On the left hand side, you have pi on top of the model, and what you get, you will at the end of the day you get the set of degrees, the Bill's degree of success in the worst case scenario. How? So you're going to have a degree of success. So you say you're gonna say the maximum value satisfied by this conditional is a member of the set denoted by this, right? And the maximum value of the maximum degree D satisfied by this is actually the degree of success in Bill's worst case scenario. Why? Because you have a set of degrees such that the organization will be successful in every single accessible world, right? So suppose that in the worst case scenario, the bill profits like 10K, and suppose that this set of degree is you plug in 11K, for instance. Then there will be a world where the organization will not be 11K successful, right? So this will basically give you the worst case scenario, Bill's worst case scenario. So what this amounts to saying as a whole is that you'll be comparing Adams' worst case scenario to Bill's worst case scenario. And the sentence is phrased to be true if and only if Adams' worst case scenario is better than Bill's worst case scenario. Yeah, these are the formal details. So, first of all, in the dominant scenario where Adams always win, well, I guess it is predicted. It makes a correct prediction, but I'm not sure whether it is making the prediction in the right way, because you're only comparing the worst cases. You're not really considering other possible degrees of success, right? You only consider where the scenario where the underdog wins. You don't even care about whether the leading candidate wins or not. And even worse, consider the deliberate risk taker scenario. So here, Adams in general wins, but there is a small chance that he will lose the bill, right? And if you compare the worst case scenarios, the sentence will be predicted as false, right? And I mean, my informant's intuition is that you either don't know, or it's true, or acceptable, or assertable. So the scenario is that, high chance of success for Adam, and Adam will be profiting much more, significantly more than Bill. Let's say 90%. There's like a 90% chance of Adam beating Bill completely, and there's 10% chance of Adam losing to Bill. And you say if Adam takes the lead, the organization will be more successful than if Bill takes the lead. So so Heim theory will in this LF will predict that this is false, but that's not what people get, as far as I know. So let's move on to second LF, where the pi operator in the embedded clause is sloping below the Biscuit model. So in LFL, this pi used to be up here, now it's down here. Everything else remains the same. So this will give you Adams' worst case scenario, and this will eventually give you Bill's best case scenario. Why? Well, you're gonna quantify over every accessible world where Bill takes the lead, right? And this is the organizing degree of success. You say that this degree of success is a member of this set. And what is that set? So in every epistemically accessible Bill takes the lead world, you're going to have the degree of success, and that's actually less than Adams' worst case scenario. That's 50. So yeah, we may have pi down here. Yeah, it's going to give you a stronger read, right? Because you're comparing Adams' worst case scenario to it should be Bill's best case, as far as I know. That's the typo, right? Sorry. So it's the Bill's best case. And if you think about it, even if you compare Adams' worst case scenario to Bill's best case, now even the dominant scenario is from that, right? Because in the dominant scenario, Adams always wins, but in Adams' worst case, it's actually worse than Bill's best case, right? And one might say that we should do some kind of state-wise comparison, right? As you do in this theory, but why would you have this this inferior considerations in the first place in dealing with conditionals? That I don't know. Yeah. And it happens that Schwarzschild Wilkinson's interval-based theory makes the same prediction for this. Why? Because they predict that the sentence is true just in case there's an interval containing Adams' organization degrees of success, and there should be a largest interval which is some distance below that the other interval which contains all the degrees of Bill's success. So there can't be any overlap between the degrees of success, right? So that's basically Heim's LF2. And since and also it makes the wrong prediction, and Schwarzschild's A analysis or unit zero negation that will also make the wrong prediction. Why? Well, first, so negation always goes below Bill. So when I say I will not go to school, negation is actually below the quantifier, no? So you're gonna have the negation below the quantifier. And what this says is that in every accessible world in which Adam takes the lead, there exists a degree D such that the organization is D successful under Adam's leadership, and in each epistemically accessible world where Bill takes the lead, it's not the case that the organization's success under Bill's leadership meets that degree D. So again, there should be no overlap between these two variables, basically. So it will also make the wrong prediction for the dominant scenario and also for the deliberate risk taker scenario, right? Because in the deliberate risk taker scenario, both Bill's best case and worst case are the same because Bill is risk averse. Adam, he's a risk taker, in general very successful, but there is a tiny chance that he will fail. And if you compare Adam's worst case to Bill's best case, Bill's best case is still better than Adam's worst case. And lastly, best predictions. So regarding this, Beck makes the same prediction. So the maximally informative interval for the Dan class will be, so you're gonna have an interval containing Bill's degrees of success. And the maximum value, well, I guess it depending on the content, it could be the Bill's best case or worst case, right? In general, it should be Bill's best case scenario. And you're gonna get that degree and compare it to Adam's degrees of success. So that will basically give you the same prediction as Schwarzschild Wilkinson, Schwarzschild, and also Heim regarding LS2. So it makes the wrong prediction. So I guess we've done LS1 and 2. Now LS3 and 4. Here you have the Dan class not scoping over everything. The Dan class starts here, T2, and there's a short movement to here below the matrix efficiency model. And it happens that LS3s and 4 are identical to LS1 and 2 in terms of their interpretation. Why? How much time do I have?
How much time? Another hour, right? So when is his class start?
2:30. So
2:30, so yeah, you have.
But you have until 4, so you're just then eating into your discussion session.
okay, then I'll try to do LS3 and 4 at least. I'll take out LS5 and 6 less. So yeah, here what you're gonna say is that you're gonna first quantify or best accessible worlds where Adam takes the lead, and now you're gonna assess the rest, right? And what is this? On the right hand side, this is the organizing success under Adam's leadership, right? And so this is a set of degrees less than the organizing success under Adam's leadership in a single world, right? And this part, this is high. This is basically Bill's worst case scenario. So what you're doing is, in each world, accessible world where Adam takes the lead, you will compare the organizing success in that world to Bill's worst case scenario. And since you're doing it for each epistemically accessible world where Adam takes the lead, again, you're comparing Adam's worst case to Bill's worst case. Get it? There will be several degrees of success for Adam, and you had and this the Dan process will basically give you Bill's worst case scenario, degrees of success in Bill's worst case scenario. If you compare it to each degree of success in the Adam world, Adam takes the lead world, if Adam always wins, then Adam's worst case is better than Bill's worst case, right? That's basically. And LF4 is where you have the pi operator scoping below the embedded veil. Then this will give you Bill's best case, and since the rest is the same, what you end up doing is you compare Adam's worst case to Bill's best case, right? That's the video we already talked about. LS5 and 6, what's different here? I think the pi is higher up. The pi operator in the matrix clause used to be below the model, now it's above the model. So it raised from here to here. And this basically gives you the same reading as LS1, where you compare Adams's worst case to Bill's worst case. This side, the left-hand side remains the same. That's we're talking about Bill's worst case here. On the right-hand side, you have this will be a set of degrees such that so D, the pi operator will take the max of this maximum D, which satisfies if Adam takes the lead, the organization will be D successful. You're gonna get the maximum D, that's Adam's worst case. And you're gonna plug in here, and the entire thing will be a set of degrees that are less than the degree of success under Adam's worst case. And that's LS1. And LS6, where you have a pi in the index clause below the model, that will give you Bill's best case, and this will give you Adams's worst case comparative. You're still comparing the Adams's worst case to Bill's best case, which we already discussed. So yeah. So these are all possible scope of configurations based on Heim. And I think this is pretty much every single possible reading you get based on existing theories on the interaction between conditionals and quantifiers and comparatives. Because the field has been trying to restrict the reading to avoid overgeneration, not to produce more readings. And yeah. So I will try to respond to potential objections. Well, maybe you might want to compare Adams's best case scenario to Bill's best and worst case. Well, that will not work. Consider the scenario 34, which I call the gambler. Adam is a poor risk taker, and Bill prefers to play it safe. It is highly likely that the organization will profit significantly less under Adams's leadership than under Bill's. Although Adams's risk-taking strategy could still lead to great success. So he's a gambler. Low chance of great success, but still significant success. Or he just underperforms. And you say, if Adam takes the lead, the organization will be more successful than it will be if Bill takes the lead. If you compare Adam's best case to Bill's best or worst case, Adam being a gambler, he will in general fail, but there's still his best case is actually really good. So this should be false. I think this is false, or at least not acceptable, or not acceptable. Less acceptable. But yeah, when you try to compare best case scenarios, this will be printed as true. So we don't want to just talk about best case scenarios. Maybe you can insert a silent operator like a generic operator, and maybe say that, well, that sentence we've been talking about has the same reading as in 36. If Adam takes the lead, the organization will generally be more successful than it still takes them. That's something what these managers in general like to do instead of silent operator. But it seems like this has a slightly different truth condition. Maybe I'm not sure whether I should say truth condition, maybe slightly different interpretation. So, for example, I think I have a counterexample here. So, consider a slightly revised context where Adam is a mediocre risk taker, and the chances of great success under his leadership are only slightly better than a toss-up, let's say 60%. As before, Bill adopts a risk-averse strategy, and I consulted many people, and they say this sounds. So when you have generally in it, when you say if Adam takes the lead, the organization will generally be more successful than if Bill takes the lead. That sounds fine, but if you leave out generally, people didn't really like it. There's only a 60% chance of Adam's success, great success, and you say if Adam takes the lead, the organization will be more successful than if Bill takes the lead. People didn't like it. So my point is that I'm not really trying to go into all these series of generics, but there seems to be two distinct readings. I mean, they seem to have a distinct interpretations. When you have generally in it, it feels somehow weaker. I don't know why I can't talk about generics, but they are different sentences. Same goes for likely. So if Adam takes the lead, the organization will likely be more successful than if Bill takes the lead. Feels weaker. You can permit more exceptions in general. That's the intuition. Last potential objection. Maybe you want to distinguish assertability from truth. You might have noticed I didn't keep saying truth, false, true, false, assertable, acceptable, and so on because of this. Well, I mean, so regarding the serial conditionals, when you do a probability talk, it has been mostly discussed in terms of assertability or acceptability, right? Rather than its truth conditions. And maybe one could say that, yeah, the sentence that we've been talking about is assertable, although it is false, something like that. However, it would be conceptually odd to state that a conditional statement is true, but not assertable, right? Maybe you could say that it's false, but you can still say it. But it's weird to say it's true, but you cannot say it. And consider the following scenario. Suppose that Adam is a strategic decision maker whose choices are likely to lead the organization to great success, whereas Bill is mediocre and will consistently generate low profits. While it is possible that Adam's decisions will lead to failure, you still believe that his organization will profit just as much as it would under Bill's leadership. So Adam's worst case and Bill's best and worst case a match, but in general, Adams will be better than Bill. And I think 38 is false. If Adam takes the lead, the organization will be equally as successful as if Bill takes the lead. That's false, right? Adams is in general better. And or at least it's not assertable. Unassertable. It's not assertable. But based on LF1 and LF2, this will be predicted as true. Because you're compared in LF1, you compare Adams' worst case to Bill's worst case. They coincide. In LF2, you compare Adams' worst case to Bill's best case. They coincide. So if you're just thinking about worst or best cases, then 38 will be predicted as true, but yet is false or at least unassertable. So when you want probably talk to me about assertability, this will be unassertable. But the theory, but still the quantificational theory will predict that this will be true. It's true but unassertable, and that's weird. You can do the other way around. It could be false but still assertable. It's weird to say it's true but not assertable. So, but I'll talk about assertability a bit more later. So, what is the source of the problem here? Well, what we have done is we combine a quantificational theory of conditionals with any theory of comparatives. So maybe we can play with the theory of comparatives and fix the issue. I don't know, so you can give it a try. But what I'm going to propose is that if we drop the assumption that conditionals are quantifiers over a possible world, if we drop that assumption, then maybe we have a very intuitive working solution. So I can imagine two possibilities. One is based on scholarly theory and semantics of conditionals, where quantifiers are evaluated in the closest world, a unique closest world. So it's not a quantification analysis, you just have a single closest world. And you can say that any probabilistic consideration is maybe assertability. That's one pass. The other pass is to say that the conditionals they denote expected value, where it's the expected value of the consequent given the antecedent, and conditional probability will be given as a special case of this expected value. And before I talked about it, Stefan also talked about it, and 20 years ago, I think.
Oh my god.
Exactly 20 years ago. It was published 20 years ago. So that is
It feels like yesterday.
yeah. So it was really clever to say to was able to avoid like trivial results by having the value of a conditional being basically a conditional probability stuff. And so that's also the route I took in my recent paper, and I'll elaborate on it soonish. But let's first talk about the Stolker route. So one could reasonably argue that the conditional example at hand compares 2 degrees of success in the closest Adam takes the lead world and the closest Bill takes the lead world. And you can say that the sentence clearly has a truth value, but given that we do not know which world we are in, right? We don't know whether the sentence is true or false. That's the path Hawthorne took and also Benefit took. So yeah, so that's why some philosopher, I guess that's why some philosophers said, I don't know, to judging the sentence. Yeah, so in this way, we're not gonna just talk about best cases, worst cases. We're gonna have the closest worlds where where you can compare all degrees of success, right? That's the first route you can take. But it seems that simply replacing the quantification theory with Stolker theory will not make the analysis sufficiently sensitive to how much better or worse additive decisions are, or how likely additive organization is to outperform or underperform. So suppose it is fairly more likely that the organization will profit more under Adams's leadership than under Bill's, but the gain is only marginal. Also, assume that in Adams's worst case scenario, the organization suffers in immense loss, whereas Bill, in consistently risk-averse as always, never poses such a risk of failure. So, in general, Adams is slightly better than Bill. Adam is slightly better than Bill, but there's still a chance that Adams will just go down. Then you say, if Adam takes the lead, the organization will be more successful than if Bill takes the lead. I actually would appreciate your judgment. So in this context, I find it more odd to accept 39 compared to where Adam is a very good risk taker. But let me know if you don't agree. Yeah, I can read.
Oh.
I could just better illustrate for the audience here.
Sorry, does anyone have a marker?
No, it's okay. But
yeah, I'm sorry.
You guys all very smart enough. It's smart and smarter to think about this in defense. Okay. So this is like Adam is slightly better than Bill in general, like 90% chance of being better. But in the worst case, there's 10% chance that he will just fail. And you say if Adam takes the lead, the organization will be more successful than if Bill takes the lead. I don't like it. At least less. I like it less than when Adams is a very good one. Of 90% chance of having a high success and 10% chance of failing. I think I'm not an speaker, but I sense a contrast here. So I thought maybe somehow we should really think about not just about like how likely Adam will be better than Bill, but how much more Adam will be better than Bill. So the likelihood and the degree of success, they somehow have to be considered together. And if we take a Stolker route, you can still do this within the assertability domain, if you want to, right? In what follows, I'm going to present an alternate solution where you build this all into the truth condition, the semantics. But what I say could potentially be implemented as a theory of assertability. But yeah, depends on how much I proceed. So So I'm gonna make two assumptions. So one regarding conditional, the other one regarding comparatives. So I will hypothesize that conditionals denote expected values. Where conditional probability is a special case. And yeah, as I already said, in the linguistic literature, the value of a conditional has been discussed in terms of conditional probability with more. So, for instance, Kaufman, 2005, and following works. It's more complicated, so I decided to stop by. But there's also Lasser, 2011, 2020, 2017 or something, where if phi then psi is true, just in case the conditional probability of psi given phi exceeds some appropriate threshold. And recently, Chung and Macarius, that's D, raised the possibility that conditional denote the expected value of the consequent given the antecedent, and conditional probability is obtained as a special case when the consequent is proposition denoted. So the idea was I didn't really give like natural language evidence, but what I said is that you have a Korean modal construction where the Korean modals are usually conditionals. So when you say you must phi, and you got to say only if phi, then suffice. So you have an only if conditional we say that is predicate. And what I have shown there is that on the deontic side, if you take the evaluated predicates of phi will be a measure function, and you have a conditional. And if conditional denote expected values, you combine it, what you get is a theory which compares expected utilities for the truth condition of must, deontic must. And on the epistemic side, you do the same thing but you have a different way to interpret the measure function, because it will be related to facts and evidences, piece of evidence. Then what you get on the epistemic side is basically a measure of Bayesian competition. So what I said is that, yeah, if conditionals denote expected values, then we get a very nice connection to expected utility theory, Bayes theories, and also the literature on Bayesian confirmation in epistemology. So we and they will be connected via modal reason. So that was the point. But I didn't really give like natural evidence that conditionals are expected value. In any case, so this is basically in line with Kaufman's works in the sense that conditionals themselves do not have a truth value, but they denote a degree. So yeah, so so you say if phi then will psi, you're gonna get expected value of psi given phi, and this in general. So if this psi is proposition denoting, it will have a truth value. It will value to 0 or 1, true or false, and then the expected value calculation will be used to the conditional probability of psi given phi. And if you want to convert this to a truth value, then what you do is you just use a fractional operation, which Lasser uses to convert degree denoting modal auxiliaries, such as odd and should, to a truth value. So when you for should, let's say odd, deontic odd, and you say like phi, odd phi, you're gonna get a expected utility of phi. Then compared to a constituent determinant threshold, and if the expected utility exceeds that threshold, then all phi is true, something like that. So this fractional only operation has been widely used, and I guess not in linguistics, but more in psychology. And one thing is, what I kind of deviate from Kaufman, although not entirely, because here I talk about expected values, is that if the consequent is not proposition denoting, for instance, if it's a vector function, what you get as the expected value of psi given phi is the expected degree. Sometimes it's degree. So if psi is a measure function, say a degree of success, if it returns a degree of success, then what you get as the expected value is the expected degree of success. That will be the main point. And since this calculation of expected value takes account both the range of possible degrees of the organism's success and their associated likelihoods. I think the resulting theory will be at least be more sensitive to the likelihoods and degrees of success. How much more successful. So it will not just consider maximal or minimum. It will also consider degrees in between and the likelihoods of it. And that was my first assumption. Conditional below degrees, expected degrees. And the second assumption regarding comparatives is that basically due to Kennedy and McNally, that comparatives are difference functions. So what Kennedy and McNally observed in the past is that so when you say much will only much can only modify absolute adjectives based on their observations. But it's weird. Tall is a relative adjective, but when you have a comparative like taller, all of a sudden you can say much taller. That was one puzzle. And what they conjectured is that the comparative is actually converting any, for instance, relative adjective to an absolute adjective by taking the difference between what are compared. When you say John is taller than Bill, you're not gonna, so in their perspective, you're not saying that John's height exceeds Bill's height. Right? It will end up saying it, but what they do is first they're gonna subtract Bill's height from John's height. That's the new measure of height. And you say that's greater than the threshold, which will be given by Bill's height. Bill's height is the 0 point, and John's height, and what you get as degree is that the difference between John's height and Bill's height. That's the degree you get, and you compare that to Bill's height. That's a 0 point. So you're basically subtracting, right? All the difference function. So this has been implemented in signal years in Kennedy 11, and Grado and Kennedy. And yeah, I'll skip this. It's basically saying that you're going to subtract between 2 degrees to get a comparative. And yeah, I'll just skip this more. And so Grado and Kennedy has a more complicated analysis where these like compare the difference function is basically a feature. It's like a morphological feature. There are several interactions. But yeah, that is all orthogonal to what I'm going to say. So I'm going to merge them all and say that comparatives will just be subtraction. And here, so more. So when you say John is taller than Bill, you're going to get tall, and that's the Bill's height, and that's John. You're going to enter John, and you're going to say that more tall, John is more tall than Bill. Will give you John is more tall than Bill. Will give you the degree, which is the difference between John's height and Bill's height. And if you want to convert it to a truth condition, you basically use a pause operator and compare it to the condition degree, in which in this case is Bill's height. That's a 0 point. So combine these all together. So we're going to start with the Dan cost. So we had if Adam takes the lead, the organization will be more successful than it will be if Bill takes the lead. You're going to just do the Dan cost. The Dan cost will just denote the expected degree of success under Bill's leadership. Why? Successful, I'm going to treat it as a measure function. And organization successful, when you combine organization successful, you're going to get the degree of success. Just the degree of success. And that since that is the consequent, and the conditional as a whole will be calculating probably weighted average over those values. What you get is this, which is basically the expected degree of success under Bill's leadership. That will be the denotation of that clause. And you're gonna then in the matrix clause, in the consequent of the matrix clause, that's the organization will be more successful than it will be if Bill takes the lead, right? So you have a comparative, and in each WA, that's the world where Adam takes the lead. In each WA, you will be subtracting the organization success in WA. You're gonna have the organization success in WA, and you're gonna subtract the expected degree of success under Bill's leadership. That's here. that will happen within the consequent cost, and then you're gonna basically calculate probably weighted average over that. And what that gets you is the following. So the matrix structure. So this is Bill's expected degree of success. You're gonna subtract this from a single degree of organizing success in WA world. That's a world where Adam takes the lead. And then you're gonna have a probably weighted average over all of that, assuming that Adam takes the lead. And you just calculate, derive it, and what you get eventually is that you're gonna get a difference between the expected degree of additive success and the expected degree of Bill's success. And the difference should be significantly high. That's what you get as the analysis of the conditional at hand compared to condition method. So basically this says that this sentence in 50 is true or assertable if you take this analysis as an assertability condition. The sentence will be true or assertable as long as Adam's expected degree of success is significantly greater than Bill's expected degree of success. Sorry, that's say. And this is indeed the case in the dominant scenario and the deliberate risk scenario. Why? In the dominant scenario, Adam's always wins, so Adam's expected degree of success is greater than Bill's expected degree of success. In the deliberate risk scenario, Adam had like 90% chance of great success, 10% chance of failure, Bill's mediocre. So if you think about their expected degree of success, Adam's will be higher than Bill's. So far so good, but it's not perfect. For instance, this is what I still haven't been able to solve. So what my analysis does penalize unlikely possibilities, right? Because when you calculate expected degrees of success, unlikely possibilities will have a smaller weight. So I penalize them, but it still predicts that the example will be true if the expected degree of additive success is significantly greater than that of Bill's success. And this could be possible if additive upside is immense. So suppose that, think about the gambler case, where there's like 10% chance of great success and 90% chance of failure. And Bill's risk-averse. But if that degree of great success is really great, then the expected degree of additive success will still be quite high. I cannot avoid that, right? That's no concern. So the gambler in the gambler scenario, if there is like such an immense degree of success for Adam, although unlikely, it will be predicted as true or assertable. So it shouldn't be that extreme. So that's no concern. And there's another issue, which is that in the deliberate risk taker scenario, the context already makes clear that Adam could fail, right? Right, Adam, like there's 10% chance of Adam failing, but here, if you look at 51, so when you just say it in the assertion, it is possible that the underdog will win the election. But if Adam takes the lead, the organization will be more successful than if Bill takes the lead. So some philosophers say this is odd, and I don't have intuition. So, do you agree with this? If you want, it's here. So,
Sure.
You're not sure.
Yeah.
So, Laurie, how about you? I'm sure.
Really bad.
You find it bad. And that's all because the concept already gave the possibility of Adam failing, but when you say it again, somehow degraded, and I don't know why. So that's still my concern. I have to hear your thoughts, and that's all I have.